Hi students, this is Mrs. Brunk.
Welcome to geometry and to lesson 7-1. So we just wrapped up studying about proving triangles congruent. And we are now going to be embarking on looking at, in today's lesson, interior and exterior angles in some figures like triangles, but for other figures as well. Other polygons. So our learning goal is to be able to find the measure of interior and exterior angles of a triangle. And our other learning goal is we will be able to find the sum of measures of interior angles of a polygon. So we want interior and exterior angles for triangles and interior angles for polygons like quadrilaterals, octagons, pentagons, things like that. So the first thing we want to look at is called the triangle sum theorem. So the triangle sum theorem we've been using really throughout the course. And this is a pretty widely known theorem by the time people get to geometry. And there's a lot actually that is really known about triangles before you get to geometry, because they're the most basic polygons. They are the polygons with the least number of sides. And what we know for sure about all triangles is that the sum of the angle measures is always 180 degrees. So the official name for that rule is the triangle sum theorem. Now, if we wanted to apply the information from that theorem to higher degree or higher polynomials with more sides, like decagons and things like that, we could use what's called the polygon angle sum theorem. And it says that the sum of the measures of interior, meaning inside angles, of a convex polygon, convex meaning that it doesn't have any like dents and holes in it, it's more of the typical polygon we're used to seeing, with n sides would be equal to n minus 2 times 180 degrees. So the reason why that works is this. Let me just give you a little example. So say I drew a rectangle, which actually I just did, but here's another one. And let's say I drew in one of the diagonals. Now a diagonal is a segment that goes from one vertice to a vertice on the opposite side. So right here there's a diagonal. So say I drew in all the diagonals from one vertice, okay, and that's just, in this case, just one. What I've just done is I've divided this up into two triangles, each of them with 180 degrees. Well, so it was a four-sided figure, right? And I was able to cut it into two triangles. So if you think about this formula, what it's saying is n, meaning number of sides, minus 2 times 180 degrees. That would work here. So I have four sides. If I subtract 2 from that, I get 2. And that's what I got here is two triangles. Each of them is 180 degrees. So thinking about that on like the next level, say I were to draw, I don't know, like a pentagon. So this is a pentagon. It's not a regular pentagon, meaning all sides and angles equal, but it is a pentagon. It's a five-sided figure. And if I were to take and draw, say, from this vertice all the diagonals, there would only be 2 from that vertice without them overlapping. And so what I've just done is divided it up into 3 triangles. Each is 180 degrees worth. So it was 5-sided. And 5 minus 2 equals 3. So I've got 3 triangles, each at 180 degrees. And I could continue to do this, adding more sides to the polygon till I got to say octagon. If I drew an octagon, I could split it up into 6 triangles. A decagon, which is 10 sides, I could split into 8 triangles, and so on. And so we can use this fact, which is this process, which is called triangulation. I think that's triangulation. Excuse me. That we can find that in any typical convex polygon, that we can find the sum of all the inside angles by using this formula, n minus 2 times 180 degrees, where n means the number of sides of the polygon. So keeping that in mind, let's answer these questions. So what is the sum of the interior angles of a hexagon? So first of all, hexagon. So we have to think about what each, prefix means. So hexa means 6. So this is 6-sided. Okay, so that would be 6 minus 2 times 180 degrees, which would be 4 times 180. So that would be 720 degrees. So if you were to add up all of the angles in a hexagon, which there would be 6 of them, 6 angles, the sum would always be 720 degrees. Let's see, B. The sum of the interior angles adds up to 3060. How many sides does the polygon have? So this time, they're actually telling us the sum. So we know that the sum is equal to n minus 2 times 180. And so this time, instead of giving us the number of sides, they want us to find the number of sides, and they're telling us the sum. So if I put that in for the sum, 3060, all I'd have to do now is solve for n. So step 1 would be I would divide by 180 degrees. So let's see, 3060 divided by 180 degrees is 17. So if I divided both sides again by 180, I would get 17 equals n minus 2. So then I'd have to add 2 to each side, meaning that n would be 19. So this would be a 19-sided figure. Now we don't have any special name for 19-side. We just call it 19-gon. When there are less number of sides, like there's, say, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, decagon, and then after that, it's pretty much just however many sides gon. So like 11 gon, 12 gon, 13 gon, 14 gon. And then every once in a while, they'll throw in a special name. Like when there's 20 sides, they call that like dodecagon. So that means like two decagons. So that's 20 and things like that. So they'll randomly give a special name after, but after decagon, mostly they're called whatever the number of sides, and then gon, so 11 gon, 12 gon, and so on. So as you see in C, what is the sum of the interior angles of a 14 gon? So that's 14 sides. So again, that would be 14 sides, or that's n, minus 2 times 180 degrees. So that actually really means I'm going to multiply 180 by 12. And that gives us 2,160 degrees. D, the sum of the interior angles adds up to 1,080. How many sides does the polygon have? So that's really similar to B, but this time they're telling us that the sum is 1,080, and we have got to find n. So that would be n minus 2 times 180 equals 1080, and 1080, first step I'd have to do is divide by 180. So step 1, divide by 180, and that gives me 6. So 6 is equal to n minus 2. If I add 2, that's n. That means it must be n is 8 or an octagon. So this is an octagon, octa for D. So what we can also do is use this fact to find individual angles. So not just the sum, what they all add up to, but individual ones. Knowing the fact that what the whole sum would have to be, and if we knew certain angles in the figure, we would have enough information to find out any missing ones. So let's see, this figure, and sometimes these are hard to count, so I think it's easier just to kind of just put numbers around them. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9 sides, which is called nonagon. And so I know that the sum of these angles would have to be 9 minus 2 times 180 degrees. So that means that the angles have to add up to 1,260 degrees. Well, if we take each one of these angles and we subtract from that, that'll tell us what that unknown one is right here. This is x, because if they have to add up to 1260, and we just subtract each one of these, so I could subtract, let's see, starting as I go around 125, then I could subtract 130 from that, 172, there's a 200-degree angle, that doesn't even make sense. It can't be 200. There's no way that angle right there is 200, so there's a little error on this problem. We'll see if we can figure something out. But that can't be 200 because that's not even over 180 degrees. So something's not quite right with that. We'll have to figure out what's going on there. That's got a problem. And then 98, and then 135. Huh. That doesn't seem to really make sense, but that would actually leave us 158 degrees for the missing angle. So that just looks mislabeled. There's no way that that angle could be 200 degrees. So, but we're just going to assume it is, and that would leave us with 158 degrees left for this to be. An example B here. So this is actually a really good one to look at, why this n minus 2 times 180 works. If we were to draw in the two diagonals from this vertice, so you can split that into 3 triangles. So we actually know that all of these angles in this figure add up to, because this is a 5-sided figure, so that's 5 minus 2 times 180, so that's 3 times 180, which is 500. Let's see, I think it's 540. Yep, 540. And if we go through this figure, we'll see that we have 1, 2, 3 right angles. So we can subtract 90 3 times, right? Which is going to leave us with 270 degrees left. So actually, if we wanted to write an equation for this, we could say this. We could say 540 degrees is equal to 90 plus 90 plus 90 plus x plus x. So after subtracting the 90s, we have 2x left, and that equals 270. Dividing by 2 tells us that each of these angles, that angle right here and this one over here, they're the same. They must be 135 degrees. So that's our missing angles, are each 135 degrees. See, example C says to determine the measure of the fourth interior angle of a quadrilateral if you know the other 3 measures. Okay, so quadrilateral means 4-sided. That means we have 4 minus 2 times 180. That would be 2 times 180, which is 360 degrees. So that one might be one you already know too. Quadrilaterals we study a lot, and so it's kind of common knowledge that their angles all add up to 360 degrees. So all I'd have to do is take the 360 degrees, and I'd have to just add them up. So I know that 89 plus 80 plus 104 plus this unknown angle, let's say we call it x, would have to add up to 360 degrees. So taking away the 3 angles that we do know add up to, let's see, 273. So that would be 273 that I'm going to subtract from 360. Leave me with 87 degrees. So that would give me x. So 87 degrees for the fourth angle of that quadrilateral. So one other type of problem that we can solve using that polygon sum formula is we can actually find an individual angle measure in a regular polygon of any type. So regular means all equal sides and equal angles. So if we wanted to know what each measure of an angle in a regular decagon was, so remember dec is 10. So that means all the angles in the decagon add up to 10 minus 2 times 180 degrees, which would be 8 times 180, or 1440. And then because there are 10 angles that are all the same in that figure, to find each individual one, all we have to do is then divide by 10. So that would give us 1440 for the sum divided by 10 angles. Each one of those angles would be 144 degrees. So if this instead was a nonagon, we would use 9 minus 2 times 180, and then we would divide by 9. Or if, say, it was a regular pentagon, it would be 5 minus 2 times 180 degrees, and then divide by 5, because however many sides the figure has, that's how many angles it has too. And in a regular polygon, all sides and angles are equal in measure. So up to now, we've been using facts about triangles, but we've been studying these larger polygons, these multiple sides, so 4-sided, 5-sided, 6-sided, and so on. Now we're going to really zero in back on the triangle and learn some more things about angles in a triangle. So what is an exterior angle? Well, an exterior angle is exactly what it sounds like. It's an angle that's outside a triangle. But more specifically, it's actually an angle that's formed when you take a side of a triangle and you extend it out past the angle. So in this drawing here, this angle right here is an exterior angle. There actually are 3 exterior angles in any triangle, because you could take any of the sides and extend them out. So I could take, say, this side and extend it out. Oops. I could make this side extend it out, and I would have an angle at each side. So if I extend this one out, this would be the exterior angle. This would be the exterior angle. So anyway, but the exterior angle in this triangle we're focusing on is the one here with the little arrow. And what another, I guess, definition would be what's called a remote interior. Well, you think about the word remote. So you use a remote for your TV so that it can be on the other side of your bedroom and you don't have to get up and go touch it, right? It's on the opposite side. It's not right by you where you can touch it. Well, that's what it means here. A remote interior angle is an angle that is not adjacent or not next to the particular exterior angle that we're focusing on. So in this case, the exterior angle right here and would be that's that at that vertice, but then the other 2 angles on the inside would be the remote interior. See, they're on the opposite side of the triangle. They don't actually touch the exterior angle. So those are called remote interior angles. And that's important to this definition we're going to learn, which says this: the measure of an exterior angle of a triangle is equal to the sum of the measures of the remote interior angles. So in other words, in this drawing, these 2 angles, so here, this one and this one, if I add them up, they will equal the exterior angle. And the reason why that is, well, first of all, the interior and the exterior angle. So say I looked at these 2 angles, the interior and the exterior angle at this vertice, those 2 angles make a linear pair. So they add up to 180 degrees, right? And also we know that the 3 angles inside the triangle add up to 180 degrees. And so because of that, because that relationship that the linear pair adds up to 180 and so do the three angles, then that exterior angle must be the value, the sum of the two remote interior angles. So how are we going to use that? Well, that if we know, say, the two remote interior angles, we could use it to find an exterior angle at the other vertice or vice versa. So looking at a couple simple examples in A, if I wanted to find the measure of VWX, so VWX is this angle, I'm sorry, VWY, my fault. So that's this angle here, this remote, not remote, but this exterior angle. We're going to look at the two remote interior angles, and all we have to do is add them up, and they will equal the exterior angle. So that means I'll take the angle at Y, which is 40, and the angle that's at X, and that's 80, and add them up, and that's 120 degrees. Now that makes sense because you think about this. If that was 120 degrees, right? So that was 120. Then the angle inside, so if that's 120, the angle next to it would have to be 60 degrees because they have to make 180 degrees as a linear pair. And then that would work with the other two angles to make 180 degrees in the triangle. So it makes sense that the exterior angle would be 120 degrees here. So in this next example, they actually want us to find the measure of angle L. Well, what I know for sure is that angle L and K, if I add them up, they equal this exterior angle, which is 130 degrees. Well, if I wanted to write an equation that said that, I could just say that angle L plus angle K, which is 65 degrees, is equal to 130. And then all I have to do to find out what angle L is just simply subtract 65 from both sides. And in fact, I find out that angle L is the same as angle K. In this case, not always true, but in this case it is. It's 65 degrees. So those two angles are the same. So 65 degrees. Sometimes we'll throw in a little bit of algebra, so not just arithmetic, which is what we were doing in those two problems. So in these final two questions, we'll have to write and solve an equation to actually find a value of a variable so that you could find the measures of some angles in these diagrams. So here's the exterior angle, right? It's on the outside, and it's equal to 3x minus 8. But we know it has to be the sum, equal to the sum of the two remote interiors. So it would have to be equal to the sum of 90 and the other angle, which is x plus 2. So there you go. We've got a equation now that's a true statement that we could use to find out what x is and therein find out what those angle measures are. And the angle they actually wanted me to find was PRS, which is the exterior angle. So that's what we're trying to find, is the exterior angle. So step one is I'm going to clean up the right-hand side. So when I add the 90 and the 2 together, that makes 92 plus x equals 3x minus 8. So we want to get all the variables on one side and real numbers on the other. So I'm going to go ahead and subtract x from both sides, leaving me with 2x minus 8 over here, 92 on the other side. Now I can add 8 to get so that all the constant terms are on the right. So that gives me 2x is equal to 100. Dividing by 2 would give us x equals 50. So if x is 50 and they wanted me to find this angle, well, this angle would be 3 times 50 minus 8. So that's 150 minus 8, or 142 degrees. Now, if I knew that that angle was 142 degrees out here, then I could go ahead and find all the other angles as well. I could find the angle next to it because these two make a linear pair right here. And then I could also find the angle that's labeled as x plus 2. It's just going to be 2 more than that, which would be 144 degrees right here. So they didn't ask for those, but I certainly could find them very easily. So keeping that in mind, we're going to leave this last one to be our you try question. I'm going to have you give this one a try. And you try question. And when we get to class, I'll have you share with me the answer that you got. So be sure to do this one, because first thing when we meet in class, first thing I'm going to do is ask you to tell me the value of z and then find the measure of angle B. So you're going to find what z is, and you're going to find what the measure of angle B is. Okay? So that does it for today's lesson. Make sure you complete your you try question, and I'll see you in class.